Okay, we're good now. Hopefully no one who isn't here wanted that problem. Okay, are there any questions on what I just did? If there are questions, feel free to ask. If not, I'm just going to move right along. Okay, sweet. So let me go ahead and check. Oh, wow. There's a lot of questions now. It's great. I just didn't expect it. So I know the next one was 48A and B. Yeah, there is a link. Hold on. Let me just so this Google Drive will have the Jamboard in it, and it's just the chapter 4 study session Jamboard. It also has in it like the document of the important theorems. All right. So let's go ahead and just do 48A and B. Okay. Oh, good. Okay. I think there was a question on Newton's method as well in there. So let me just look at that. So someone said, will there be a problem where we need to use our calculator for Newton's method? I am not 100% sure. Since it's on the study guide, I would assume that it's something that you probably should know how to do. And I can totally give like a little tutorial again on how to do it on your calculator. I would just say anything on the study guide's fair game.
Kaylee, he in our class was pretty explicit about us not having to use a calculator.
Oh, okay.
So I don't think there will be, but he said today his answer to that question was, well, I told you in another class you would only solve for X1 and you wouldn't use a calculator. So,
Got it.
But if you want to do it, I'm sure we would all watch.
Okay, no, that's good. And that's what I thought because I was pretty sure that like usually on exams you were never like told to use a calculator, which is like interesting because in my mind just take it off the study guide, but like that's good to know. So yeah, I'll do it by hand because I think part A of 48 is by hand and then B is use a calculator. It doesn't take too long to do the calculator portion, so we can just do it. It's good to know. Okay, so let me, okay, so 48A, so yeah, part A is without a calculator. Okay, so Newton's method, there's a little theorem. I'm just gonna write down exactly what the theorem says, and it is in that little cheat sheet, I guess, that I made. So Newton's method says that xn plus 1 equals xn minus f of xn over f prime of xn. Okay, in order to like do Newton's method, I feel like you really need to understand what it's even doing. Because if you don't understand what Newton's method is, this probably just seems completely pointless. So Newton's method is approximating a root of a function. So if I give you a function and you give me an initial guess at what a root of the function might be, you can use Newton's method to basically get to the root. So essentially you start with a guess and your initial guess at what the root should be needs to be as close to the actual root as possible. And then Newton's method just basically gets closer and closer and closer to what the actual root is. And if this sounds really dumb and pointless, it's actually not because I use this in some of my classes. So it's actually interesting. But anyways, that's what Newton's method does is it approximates a root of a function. And it's like in what's called an iterative method. So basically to find the next approximation, you really just need the one before it. And you can see if you're trying to find x sub n plus 1, the only thing that's in this equation is x sub n, which would be the guess before it or the approximation before it. Okay, so let's go ahead and do that. So it gives us the function and then our initial guess, which is x naught. So x sub 0, x naught, that's just your initial guess at what the root is. So to find x1, I need x0 plus f of x0 over f prime of x0 or x naught, whatever you want to call it. Okay, and this is equal to 3 plus f of 3 over f prime of 3. So I'm just plugging in 3 because that's my initial guess. So I do need to go ahead and actually find the derivative because I have f prime of 3. So if this is f of x, the derivative of f of x would just be 3x squared. Okay, and then to go ahead and finish plugging in things to Newton's method, I need f of 3 and f prime of 3. So we'll do f prime of 3 first. And f prime of 3 would just be 3 times 3 squared, which is going to give you 27. And then we also need f of 3. So f of 3 is equal to 3 cubed minus 10. And that's just going to give you 17. Okay, so now all you do is plug everything in that you have. So this is 3 plus, and f of 3 was 17. F prime of 3 was 27. And then you do want to make these into one fraction, so you actually do want to add them together. So to do that, you'll need to get a common denominator. I won't go too deep into the algebra, but this is 81 over 27. Let me make sure that's right. Yeah, that's right. Okay. Plus 17 over 27. And that would give you 90. Oh, wait. Would it be minus? Oh, it's a minus. I'm so sorry, guys. I accidentally copied everything down as a plus. This is a minus. My apologies. This should totally be a subtraction. It's my bad. I knew something seemed wrong. Okay. And then this is, let's see, 70. So what? That gives you 64? Yeah. 64 over 27. Okay, my bad. Totally copied the formula down wrong. But that would be your x1. And that's how you do it without a calculator. You literally just use this formula. And let's say that they asked you to also compute x2 by hand. You would do the exact same thing, except now you'll use what you just calculated for x1. So Newton's method is not terrible. It's the same formula, and you just repeatedly do it. So because I know that Amber said, at least in one of the classes, you will not have to use a calculator. I don't know about both classes, but does anyone care to see me do part B? I'm not sure if Eric's class is potentially letting you use a calculator on the exam, but I mean, if anyone wants to throw something in the chat, you could tell me. If one person wants to see it, I'll do it. I don't care. I just don't want to waste anyone's time if they don't want to see it. You don't think he is? Okay. Okay. Well, if we don't think he is, then I won't do part B. However, if we're done and someone wants to see it, I'll totally do it at the end. It's kind of fun, but it's
So
not on
just
the
to make sure
exam.
I can understand how part B would go. So you just plug in 64 over 27 to the functions and all that and just keep iterating from there, correct?
Yeah.
Okay, perfect. Thank you.
Yep. So essentially you type in what we got, 64 over 27, and then you basically tell your calculator what to do and just keep hitting enter, and it will keep doing successive, or oh, that word's hard, approximations. So anyways, I think this is important though. The question in 48B, it says, what value are you approximating? That's kind of important to realize that, don't lose sight of what you're doing. Like I said, it can kind of seem pointless if you do, but you are approximating a root of a function, and you're approximating the root of f of x equals x cubed minus 10. And the root of that is just where it's equal to 0. So you're approximating where x cubed minus 10 is equal to 0. And that would just be cubed equals 10. And that would be the cube root of 10. So just don't lose sight of what you're approximating. And the cube root of 10, if you wanted to use a calculator, is about 2.15. And the guess that we had above here, 64 divided by 27, is 2.37. So it's really not that far. It's a good method, and it works pretty well. So that's my speech on Newton's method. Okay, let me see what the next question is. Okay, 22 and 23. And feel free to interrupt me if anyone has any questions. Sometimes I just get talking and I'll just keep going and I forget to ask if people have questions. Yes, some good old optimization problems. Okay. All right, so yeah, these ones are everyone's favorite. Everyone loves a good word problem, right? Okay, so it says for questions 22 through 25, write the equation to be optimized, the constraining equation, if necessary, and find the critical values of the function and verify that your answer is the value that optimizes the function. Okay, so this gives you very specific instructions, which is always good for an optimization problem. So in general, you start with something that you're optimizing. And that means you're either finding basically always it's going to tell you to maximize or minimize something, or find the maximum blank, find the minimum blank. So first step, read the question and see exactly what it's asking you to optimize, which just means maximize or minimize. Once you do that, there's usually some form of what's called a constraint. And a constraint, I like to think of it as just like an extra piece of information that will help you go ahead and solve the problem. So identify that. And then what you do is kind of put these two pieces together. So you usually will plug the constraint into the equation that you're maximizing. And then you'll usually take a derivative, find the critical values, and that will give you a max or min. Because remember, derivatives, if we find the critical values, or sorry, if we use the derivative and find the critical values, those are places where we could have a max or min. It's not necessarily a max or min, but it's spots where we could. So if you're trying to maximize or minimize something, why not take the derivative, find any critical values, and those are possible places where something would be maximized or minimized. Okay. So 22 says that we are maximizing the product of two non-negative numbers whose sum is 30. Okay, so we're maximizing, I'll highlight, maximize the product of two non-negative numbers. Okay, cool. So I'm just going to call these two numbers x and y. Doesn't matter, but I am maximizing, and I'm just going to say p equals x times y. Like the product of these two numbers is x times y. And we're trying to maximize this. And then you can see there's another piece of information we're given, and that's going to serve as your constraint. So we're told that the sum of these two numbers is 30, and that is a constraint because that definitely affects what our answers are. If you told me the sum was 25 or the sum was 40, I would get completely different answers. So the constraint definitely, tells you what your solution will be. So that's why it's called a constraint. So the constraint is that x plus y needs to be 30. Okay, so let's go ahead now and put these two pieces together. Your next step is usually to take the constraint, solve for one of the variables, and then plug it back into the original equation. So this constraint tells me that y needs to be equal to 30 minus x. And I'm just going to plug that back in. So I get p equals x times 30 minus x. And notice that this is a function of x now only. There's no y's in it. It's just x's. So you could actually write this as p of x. Just an observation. So your goal is to take the constraint and be able to write your equation that you're maximizing in terms of solely one variable. So you only want one variable in this. Okay. Lastly, you do want to find the domain. And that comes down to the fact that whenever we find critical values of a function, we always want to talk about the domain, because if your critical values are not within the domain, then you can chuck them out. So once you find this equation here in terms of one variable, go ahead and identify what the domain is. So your domain will have to do with the information that you're given. So we're told that their sum must be equal to 30. So we obviously can't plug anything in for x that's greater than 30. Because if we plug in something greater than 30, that doesn't meet the requirements. So our domain is from 0 to 30. Anything less than that breaks the fact that these numbers are non-negative. And anything greater than 30 breaks the fact that their sum has to be 30. Okay, So I'm going to just distribute this x in just to write the function a little nicer. So 30x minus x squared. Okay, so next step is to actually take the derivative of this. So p prime of x is equal to 30 minus 2x. And then when you're finding critical values, you want spots where either the derivative is equal to 0 or undefined. Do not forget the undefined one. I see a lot of people forgetting that when I grade worksheets. So a lot of people will find the values where the derivative is 0, but forget the undefined part. And sometimes those end up being maxes or mins. So definitely find any spots where it's undefined. In our case, those don't exist. When there's spots that are undefined, usually you're dealing with something with a root, or you're dealing with something that's a fraction. But in our case, we don't have any of those, but do not forget them. So in this case, we only need to find spots where the derivative is 0. Oops. Okay, so we get 2x equals 30, and that gives us that x is 15. Okay, so that is the only critical value that we have. And the next step actually tells you in the instructions to verify that your answer is the value that optimizes the function. So even though this is the only value that we got, this is the only critical value, you still need to verify that it optimizes it and that it is the maximum. If you think back to whenever we were finding maxes or mins on a closed interval, we would take and we would plug in whatever we found. So like in our case, we'd plug in 15 back into the original function, see what we got out. And then we would take and also plug in the endpoints. And whichever like value that we got out was biggest or smallest, whatever we're looking for, that is the correct answer. If this process is a little fuzzy, go back and check out how to find maxes and mins on a closed interval. But the verification is important because it is points, and it tells you to do it. So, so I'm going to verify. And so that means that I'm going to take my endpoints of my domain and I'm going to plug that in. So P of 0 and then P of 30. And then I'm going to also plug in the critical value. So P of 15. And I'm going to see which output in my case is the biggest because I'm looking to maximize. And whichever one gives me the biggest output, that is going to be the answer that optimizes the function. So P of 0, so if I plug in 0 over into P of x, so that's like this function right here, P of x, you're going to get 0 times 30 minus 0, which is 0. If you plug 30 in here, you get 30 times 30 minus 30, which is 0. And those aren't looking too big at the moment, so I don't think those are going to maximize. Let's plug in 15. So this would be 15 times 30 minus 15, which is 15 times 15, which is going to be 225. Okay, great. So that's 225. That's clearly the biggest output. So yes, 15 is the value that maximizes the product. That's correct. So your answer would be x is equal to 15. And whenever you're doing optimization problems, don't forget that usually you have to provide them with two things as an answer. So yes, x was 15, but what is y? Because we said that the that we're looking for two numbers because we're looking for a product of two. So yes, you found x, but what is y? If you only put x down, you're not going to get full points because you didn't find the other element. So to find y, we can use the constraint, and y is equal to 30 minus 15, which is 15, and they both happen to be 15 in this case. And you're done. Any questions on number 22? Okay, I'm going to go on to 23 then, because I think that was the next question. Yeah. Okay, wow, I think almost every single optimization problem was asked. 22, 23. Oh no, 24. Okay. All right, 23. So another one, you'll see that these have a pattern about them. They all kind of are the same steps, which I believe there's a little step-by-step guide on the chapter 4 helpful theorems that I put in the Google Drive. But anyways, so 23 is of all boxes with a square base and a volume of 64 cubic centimeters, find the dimensions of the box with the minimum surface area. Okay. So we want to minimize the surface area. So that's the first thing that you want to identify. What are we minimizing? So minimizing the surface area. So you will need the surface area equation. So usually the surface area of a box is taking like, so if you have a box, you want to take the area of like all the sides. So you take the area of every side of the box and add it up. Okay. Well, in our case, we know for sure that it's a square base. I don't know if I could draw this very well. I'm really bad at drawing like three-dimensional shapes. It's not my gift. But we know that the base is square essentially. So here, this is the base of the box. So we know that the sides are equal. Okay, cool. So this is side length X and this is side length X. And that's the top and the bottom of the box. They're the same. So for surface area, we're just adding up the area of all the sides. So S is equal to, so there's two bases, obviously. And because they're square, the side lengths are all the same. So the area of this is just X squared. Okay, X squared. That's one base. If I could draw 3D shapes, I would. The other base, that's like the top, is also the same because the top and the bottom of a box should be the same dimensions. So add it again. Now you're worried about the sides. So you have to add in the area of the sides of the box. You don't know anything about the sides. You just know that it's a box and that it has a square base, but you don't know that it's like, you don't know anything about the length or like the height of the box, I guess is a good way to say it. If it told you that it was a cube, that means every side is the same length, but we don't know that. So we're going to call the height of the box, I guess, whatever you want to say, that's going to be y. So anyways, I really wish I could draw this nicely. I really don't think I can. But anyways, the height, so height of box, I'm going to call y. And so that means that the area of one side of the box would be x times y. Hopefully that makes sense. And there are 4 sides, which means that you have to add in 4x times y. It's just the equation for surface area. If that's confusing, it's probably because I didn't do a good job verbally saying it. Feel free to Google the surface area equation if what I just said didn't make much sense, and I think you'll be able to see why. So yeah. Okay, so we are trying to we're minimizing this, sorry. So we're doing the minimum here. And then the next thing that we want to identify is a sort of constraint. And so it tells you that it has a volume of 64 cubic centimeters. So the equation for volume would be just the, what is it? It's like the length, the width, and the height. You just multiply all those together. But in our case, the length and the width would both be x. So our constraint is that x squared times y needs to be 64. And that's just the equation for the volume of a box. So for the volume of the box, you just take and multiply each side length. So like you would multiply, the height by the width by the length. But in our case, because the base is a cube, the width and the length are both x. Okay, so I have a chat question that says, do you think we'll have to figure out the particular equations or do you think we'll be given them? Yeah, well, I would say if I was going based off what the study guide is, I would say you should probably know them. Plan for the worst case scenario. That's always your safest bet. So plan for you're not given any of them. So have an idea of what the surface area equation is. Have an idea of, what a volume equation is for these things. So, worst case scenario, plan for that. I'm not sure that that would necessarily be the case, but it's always a good idea just to know them if you can. And just a little advice, if you forget one of these things, if you are doing one of these problems and it tells you surface area or, volume, and you cannot remember, it doesn't hurt to ask. Like, it really doesn't hurt to go to the professor and say, I can't remember this equation. Like, are you able to give it to me? Never a bad idea. The worst thing they're going to do is say no. And at least you tried. Best case, they're going to say yes and give it to you. Just a little piece of advice. So if you happen to forget something like, something that's not calculus, surface area equation is not a calculus equation. It's just some general knowledge. And if you forget it, just don't be afraid to ask. Worst they'll do is say no. So just a little piece of advice. But for this one, we did kind of have to know both equations and then like figure some things out about them based on the stuff we were given. Okay, so let me simplify this one. So S is 2x squared plus 4xy. Okay, so like usual, we're going to take the constraint and solve for something and then plug it back into our equation. So I usually choose y, so y is equal to 64 over x squared. And I just want to point out the fact that if you do solve for the other thing, that's totally fine. Instead, you would just get like your answer for like y instead. So if you solve for the other thing, if you were to say, I'm going to solve for x, that's okay. You can do that too. Either way, you'll end up getting the same answer as long as you don't make any mistakes. Okay. So now that I solved for that, I'm going to plug this back into my equation. So S is equal to 2x squared plus 4x times 64 over x squared. And some nice things do cancel out here. So this x will cancel out with one of these x's. So you'll get 2x squared plus, and then 4 times 64 is 256. Yes, 256 over x. Okay, so this is S is equal to 2x squared plus, and I'm going to write this as 256x to the negative 1. That's because we're about to take a derivative, and you guys know whenever you're about to take a derivative, it's easier to bring things up as negative exponents. But before we actually go ahead and take a derivative, let's identify the domain here. So on the last problem, I said you were able to identify the domain based on some stuff you were given. However, we're not really able to use anything that we're given to say like, oh, my x has to be between certain values. The only thing that we know is the volume, and we don't know, not sure. So the domain here is actually just 0 to infinity. Might seem kind of weird because you're probably thinking like we could obviously not have a side length of like infinity. It's a bit of an odd concept, but because you cannot use the information you're given to say like, oh, my x value or the length of the sides of my base of my box, we don't know anything about that. So our domain is 0 to infinity. Okay, next step is to actually take a derivative. So you can also write this as s of x. But s prime of x is equal to 4x plus, or no, not plus, minus 256x to the negative 2. Okay, and then the thing that we want to do now is find where either this is 0 or where this is possibly undefined. So there's really no spot, I don't think. There's no spot in the domain where this is undefined, because the only spot where it would be undefined would be at 0, because this is the same as 4x minus 256 over x squared. And that would be undefined at 0, because if you plugged in 0 for x, you'd be dividing by 0, and that's not allowed. But our domain is 0 to infinity. So 0 is already excluded from being plugged in. So there's no spots where this is undefined. So we're just going to set this equal to 0. So 0 equals 4x minus 256 over x squared Okay, so I'm gonna move the 256 over x squared to the other side. And then I'm going to multiply both sides by x squared, and I get 256 is equal to 4x cubed. 256 divided by 4 is going to be 64. And then we have 64 equals x cubed, and then you just take the cube root of 64, which is actually just 4. Okay, so we get x equals 4. So you do need to verify this. Remember on the last problem, we were finding the maximum on a closed interval, and so we were able to just plug in the endpoints to verify that it was actually the maximum. Well, here you don't have a closed interval, and your domain is 0 to infinity. So something that you can do instead, and this is, I believe, yes, this is what is known as the first derivative test. I wanted to make sure that I was naming it correctly. The first derivative test, where it says that if your derivative goes from negative to positive, then you have a minimum. And if it goes from positive to negative, then you have a maximum. So we can go ahead and use that to verify that at x equals 4, we indeed have a minimum. So I'm going to whip out my good old sign line here. And I'm going to do a sign line for f, or did I? No, s. I'm sorry. S prime, not f prime. And I'm going to ensure that this is actually a minimum. So I'm going to put 4 here. I'm going to plug in a value on the left side of 4 and a value on the right side of 4. And I'm going to make sure that indeed it is a minimum. So let's go ahead and just plug in 1. So if I come over to my derivative here and I plug in 1, I get 4 minus 256, which is definitely negative. Okay, if I plug in anything bigger than 1, so bigger than 4, let's do like 5. So I get, let's do 20 minus 256 over 25. That would give me something positive. Like I've said before, it doesn't really matter what the output is as long as you know whether it's positive or negative. So if you look at something and you go, oh, that's clearly negative, that's fine. You don't need to like go through the process of getting an answer. So the important part is that anything on the left side of 4 is negative, anything on the right side of 4 is positive, which by the first derivative test means that this is a minimum. So this is me verifying. Yes, 4 is a minimum. Okay, and lastly, you just need to also give what y would be, because y is the height of the box. And we know that y is equal to 64 divided by x squared. So y is equal to 64 over 4 squared, which is 16, which is equal to 4. Woot. All right. Your final answer should be the dimensions of the box. So the dimensions of the box would just be 4 centimeters by 4 centimeters by 4 centimeters. What do you know? It actually ends up being a cube. After all that, it is a cube. Okay, any questions on this problem specifically? Ooh, okay. Someone wants me to do 24 as well, which I don't have a problem doing it, but I think I'm going to do a few other problems before that because this is a lot of optimization. So I will hop back to 24, but let's do something different for a second. I think I already answered the question. Yeah, there shouldn't be a problem where you need to use your calculator for Newton's method. So that one's answered. Okay, my next one is graphing problems 9 through 12. Let's see, what's 9 through 12? All right, let's do it. Which, if you're looking at the answer key, believe there was an error on question 9. But let's just go ahead and start and go through these. Okay, so below is the graph of a function f of x with a domain of all real numbers. Find the following if possible. Okay, so A is the x values of all locations of all critical points of f of x. Okay, so you need to ask yourself, what is a critical point? So actually, anyone, what is a critical point?
Is it where the function equals 0, or is it where it switches signs?
Close. It would be where the derivative is 0. So
Okay.
yeah, where the derivative is 0.
Okay, cool.
So yeah, that is a really important distinction to make. Good. Yeah, I got someone in the chat saying, yeah, good. So someone else said that if the slope of the tangent line is 0, that's great too. So yeah, there are a few different ways to define it. So if the derivative is equal to 0, that's a critical point, which, as someone said in the chat, in the chat to me, that is if the slope of the tangent line is 0, which is very helpful for if you're looking at a graph. So I just want to clarify some things because I think a lot of these get mixed up when you're going from talking about like the derivative to the actual function. So critical points are where the derivative is 0. The function does not need to be 0 there, just the actual derivative of the function. And that just means that the slope of the tangent line is 0. And if the slope of the tangent line is 0, that means that the tangent line is flat. So it means that the tangent line at that spot is horizontal. To make the distinction, it is not where the tangent line is vertical, because that is where the slope of the tangent line is undefined. And that, or sorry, I guess that is a spot. I'm sorry. Hold on. Let me back up what I was saying. So critical points, derivative 0 or undefined. So both qualify, but the derivative is 0 if the tangent line is horizontal and the derivative is undefined if it's vertical. That's the distinction that I wanted to make. So both are spots for critical points because critical points can be found if you set the derivative equal to 0 or if the derivative is undefined. So horizontal tangent lines or vertical tangent lines are spots where you would have critical points. But there's a bit of a distinction between the two, like and how you get them. Okay, so with that being said, A wants the x values of the critical points. So we just want to find any spots where the tangent lines would either be horizontal or vertical. We don't have any spots where the tangent lines would be vertical here. So we don't have any spots where the derivative is undefined. But we do have some where it would be horizontal. And here's one example, here's another example, and here's another example. So you want the x x values of like these spots. So that would be -1, 1, and 4. And then part B wants the x values where a local minimum occurs. Okay, so critical points are your like potential maxes or mins. They don't need to be maxes or mins, but they are potential ones. So like part B where it asks you, like the local minimum, look at the critical points that you just found. See if any of them are local mins or local maxes in terms of part C. So if we look at the points that we just found, -1, 1, and 4, does anyone see one that looks like it could be a local minimum?
1.
Yeah, perfect. And that's because if you look at a small area around 1, it is the minimum in that little area. It's not the overall minimum because obviously these outputs are less, but a local min just means if you look within a small little neighborhood, that's the minimum there. All right, anyone want to take a shot at C, the local maximum?
4.
4, yeah, good. 4 is one of them, and also -1 is also one of them. And that's because if you take a little neighborhood around -1, this is the maximum there. Same reason why 4 is 1. Cool. Okay, D says the x value where the absolute minimum occurs. So the absolute minimum is for the whole function. So it's saying if you look at all of the outputs for the function, where does the absolute minimum happen? Where's the lowest spot? Well, there are arrows here that continue to go down. And so do we actually have an absolute minimum?
No.
Perfect. No.
I have a quick question.
Uh-huh.
So like if one or for this function, let's say like it didn't have an arrow on the left side and it was just like a closed circle,
Mhm.
would that be considered an absolute minimum or is that not part of it?
Yeah, for sure. If your function doesn't have arrows and you can see every function output, then yes, that you can totally like use that. So let's pretend, I guess, that these were like dots here. If those were closed and your function was not, it didn't have a domain of all real numbers, so you were only looking at this segment here, which has closed dots on the end, you can see everything about the function in this little graph. Your minimum would be these two outputs here, which is what at like negative 15. Yeah, that would be your minimum, but because there's arrows, it means that it continues on all the way down to like negative infinity, which means there's no minimum. But yes, if there was endpoints, you would have an absolute minimum.
Okay, and then it'd just be both of those since they're both like closed circled, I guess.
Yes. Yeah.
Just wanted to make sure.
Yeah. Okay. Let's see. So E says the X value where the absolute maximum occurs. So anyone want to take a shot at this one?
Or
Yep. We do have a maximum here. This is the largest output that we ever achieve on this whole function. So X equals 4. Okay. Awesome. Let's look at 10. So 10 says, and this is where you got to be careful because 9 says below is the graph of f of x and 10 says below is the graph of the derivative. It's really hard to go from like one to the next. So you kind of got to like stop, really focus on what you're being given because it's really easy to like be like, oh, here's the graph of the derivative and totally get it mixed up with the graph of the function. It happens, super common. So really make sure that you read and see what the graph is that you're being given and try to translate what the graph gives you to what you're being asked. Okay, so it says find the following if possible. Okay, notice the questions are actually exactly the same as the top ones. So question 9 asks you all the same things, except for we were given f of x in 9. In question 10, we're actually given the derivative, but it asks you all the same questions. So you'll see how this is slightly different. So remember on question 9, where we said that critical points are where the derivative is 0 or undefined. So we are given the graph of the derivative. So just look at the derivative, find the spots where the output is 0 or where it's undefined. So you're just going to look, see where it crosses the x-axis, because that's where the output would be 0. Okay, the derivative is 0 here, 0 here, and 0 here. Okay, those are my critical points. -3, 2, and 5. See how the process was different. In question 9a, we're looking for the same thing. We're looking for spots where the derivative is 0 or undefined, but we're not given the derivative in 9a. We're given the function. So you need to translate what does that mean about the function. The derivative is 0 or undefined. It means the tangent line is either horizontal or vertical. So translate that to what you're given. Down here, we're asked for critical points, and we're given the graph of the derivative. So just find where the derivative is 0 or undefined. Same question, different process because we're given different information. Okay, B says to find the x values where a local minimum occurs. So here you are going to be using the first derivative test. I'm going to draw a little sine line and I'm just going to fill it in based on the function. So I'm just going to draw this here. This is f prime. I'm just going to say this is f. And I know that my critical points are -3, 2, and 5. -3, 2, 5. Okay, well, on the left side of -3, my derivative is positive. Between -3 and 2, my derivative is negative. Between 2 and 5, it's still negative. And then on the right-hand side of 5, it's positive. Okay. So find the x value where a local minimum occurs. All right, well, the first derivative test says that if I go from decreasing to increasing, there's a minimum. Okay, well, are there any spots on the sign line? Or you don't even need to make a sign line. If you can do this just by looking at the function, that's fine. I just do a sign line because I think it's a nice way to organize what you have. Are there any spots where the derivative goes from negative to positive?
At 5.
Yep. Awesome. Great. Okay. The next one is x values where a local maximum occurs. So a local maximum occurs if the derivative goes from positive to negative. So where does that happen at? Oh, there's a chat. Yes, at -3. Awesome. Okay. This wants the x value where the absolute minimum occurs. So I'm gonna try and just explain. I'm gonna try and just like sketch the function out, and I think that will kind of give you visually why the answers for D and E are what they are. So if I try and sketch the function, this is going to be rough. So, and this is not the only option. There are many options for like how you could sketch this. Okay, so I know that my function itself is increasing from -infinity to -3. And then I know that at -3, I have a maximum, and then I decrease. So I'm just gonna do a rough sketch. I'm gonna say, okay, goes here up to -3, then I decrease until 2. So I'm just gonna decrease, and then I have a derivative of 0 here. Okay, but then I keep decreasing until 5, and then I go back to increasing. Okay, so based on that information, there is no absolute max or min. And in order to really see that well, you kind of need to be able to envision a rough sketch of what this sign line is really telling you about the function. So this one is none, and this one is none, because this is increasing and this is going down to -infinity. All right. Okay. Any questions on number 10? Okay. I think I'm going to move on, and I might come back and do like part of 11 or 12, but I do want to keep going. So let's look at question 60. Sorry, it takes me forever to scroll. Okay, 60. Okay, a fun one. Down to integrals. Okay. Here. So for the sake of this test, you haven't learned any methods really of integration. You have learned how to do the power rule. So you've learned how to do, okay, add 1 to the exponent, divide by that. But besides that, you really haven't learned anything else. So we don't know anything like what to do with quotients or products. So if you see a quotient like this on the exam, it is a safe assumption that you will need to do some manipulation to actually take the integral. Your goal is to just get it to be a subtraction or an addition of 2 things, because that's really the only thing that you know how to integrate. You know how to integrate trig functions, and you know how to integrate when things are added and subtracted, but you don't know how to integrate quotients or anything like that. So it is a safe assumption, if you see something that looks like this, that you will need to do some manipulating. So let's go ahead and do that. Something that is a good first step is to, if you've got it over the denominator, maybe split this up and see if you can do anything. So make this 1 over secant plus tangent over secant. All right. And does anyone know what 1 over secant is? All right, well, it should be cosine. So this should be no worries. I'm rusty on my trig identities. So this should be cosine. So we should be able to rewrite this just using some identities here. So this is, yeah, this is cosine plus, and then tangent is also sine over cosine. And secant is actually equal to 1 over cosine. Oh, I left off my integral. D theta. Okay. So using this will help you out, and you will now get just an addition of things. So this is cosine theta plus sine theta, d theta. Okay, and now you have something that you can actually integrate. Woo! So the integral of cosine, anyone know that one off the top of their head?
The sine.
Yep. Sine of theta. How about sine? Anyone want to give me that one?
Negative cosine.
Awesome, thank you. And then don't forget the plus c, and you're done. But it is a safe assumption that if you see something like this, try and do some manipulation, because most likely you will be able to simplify it down to an addition or subtraction. All right. So that's question 60. 34. Okay. Oh man, there's a lot of optimization ones on here. But let's do 34 first. 34. Okay. 34 is a good old mean value theorem problem. Okay. So find the values of x equals c that satisfies the mean value theorem. So for 34, we're given f of x is equal to x cubed plus 1 on this interval. So obviously to do this, you got to even know what the mean value theorem says. And if you think back to when we talked about the average rate of change when we were doing things, we would take, so we used to do, I think that's my abbreviation. No, ARC, I think that's it. Okay, anyways, the average rate of change is on this interval is f of 1 minus f of negative 2 all over 1 minus negative 2. Okay, that is the average rate of change. The mean value theorem says that, hey, if you take the derivative, which gives you the instantaneous rate of change, there's at least one spot that the derivative is equal to the average rate of change, which is interesting. So it tells you, hey, there's at least one spot where the instantaneous rate of change is equal to the average rate of change. Super interesting fact. So let's go ahead and see where that happens at. So if you're ever trying to find the values that satisfy the mean value theorem, your first step is to go ahead and find what the average rate of change is on this interval, which is just the theorem that we learned, I think, like in the first few weeks. So let's just go ahead and evaluate this. So f of 1 would just be 2. F of negative 2 would be negative 7. And then 1 plus 2 is going to actually just be 3. Okay, and this is equal to 9 over 3, which is 3. Okay, cool. So we know the average rate of change over the interval negative 2 to 1 is 3. And then the mean value theorem says there's at least one x value where the derivative is equal to 3. So now you just have to find where that's true enough. So your second step is to take the derivative. So f prime of x. Who wants to give me the derivative?
3x squared.
Thank you. And now we just have to set this equal to 3 and just figure out where that happens at. So 3x squared is equal to 3. So x squared is equal to 1, which happens if x is 1 or negative 1. Okay, important last step. This value that satisfies the mean value theorem needs to lie within this interval that you were given. If it's not within that interval, it doesn't even make sense as an answer, because we said that the mean value theorem says there's one spot in this interval where this is true at, so your answers should only lie within that interval. And so that means that we're going to get rid of, wait. Oh yeah, we're getting rid of 1. Sorry, let me explain. Let me explain what I said. Yes, okay, so yeah, that's what I was just about to explain. So the chat, I just got asked about the endpoints, which I needed to say something more specific about the mean value theorem that I actually blanked on for a second. The mean value theorem says that the x value that makes this true actually has to be within -2 to 1. It can't be an endpoint. My bad. Totally forgot to say that at the beginning. So not only does it need to be in the interval, but it can't be an endpoint. So that's why you get rid of 1. I was really lost for a second on why you took out 1. But yeah, so the x value that makes this true is x equals -1. Totally forgot that it can't be an endpoint. Good catch. Okay, any questions on this? Okay. All right, so I was requested to do 24 and 25. I can totally do those two. And there's also 11 and 12 that I did not do. So let's do question 25, and then maybe I'll do question 11 and then just hop around. Let's do 25, because that was one that was asked. Okay. Okay. All right. Farmer Sue, let's go. Farmer Sue needs to enclose a rectangular region on her farm. She has 1,000 yards of fence and needs the region to have 4 equal sub areas as shown below. What dimensions maximize the area of the rectangular region? All right, step 1. What are we maximizing? We are maximizing the area of the rectangular region. Boom. Let's write that down. So we are maximizing the area of this rectangle, which conveniently has been labeled for us as x and y. So the area is a equals x times y. All right, then you have a constraint. It is a subtle constraint, but it is the constraint. So let's go ahead and I'll write that over here. It is subtle because it says that she has 100 yards of fence. And so you know that whatever you use to enclose this, this region with the 4 sub areas needs to total 1,000. So we know that, sorry, here is, let me use a highlighter. Here is 1x because each of these lengths is x. So 2x, 3x, 4x, and 5x. So we know that 5x plus, and then we have 1y and 2y, plus 2y needs to equal 1,000 because we only have 1,000 yards of fence. And we want to make 4 sub areas, which means that we should have 5x plus 2y, and that should be equal to 1,000. All right, so let's go ahead and solve this for y. I just always pick y, but like I said, you could pick x. 2y equals 1,000 minus 5x. Y is equal to 500 minus 5 halves x. Okay, plug this into the equation that you are maximizing. So a equals x times 500 minus 5 halves x. And now this is solely in terms of x, so I'm going to write it as a of x is equal to 500x minus 5/2 x squared. Okay, so now let's come up with a domain and figure out what that is. So before we take a derivative, let's find the domain of this. So the domain is a little subtle here as well, but it is actually going to be 0 to 200, and I will explain why that is. Okay, so we have 1,000 yards of fence. We're looking for a domain, which is values that we can plug in for x. So we know that there are 5 x's involved in enclosing this region. So if we have 1,000 feet of fence, sorry, not feet, 1,000 yards of fence, and we have 5 lengths of x, if we use every single like yard of fencing on just the x's and none of the y's, that would be 200 yards per x. If we use none of it, then that's fine, but that means that our y would be 500 each. So the domain is 0 to 200. If you can use none of it. I mean, it doesn't make a very good region. Or you can use all of it on just the x's, and that means that each of them is 200. Okay, so now let's go ahead and actually take a derivative. So a prime of x is equal to 500 minus 5x. This is actually not undefined anywhere, so we're just gonna set it equal to 0, because right now we are finding critical points so that we can find a max or min. So this isn't undefined, so you're just gonna find where it's equal to 0, which is at x equals 100. All right, you probably noticed this is extremely similar to question 22, because you're dealing with a closed interval. The verification process is the same. So just for comparison, it's pretty similar. So to verify that this is where the area is maximized, we're going to do exactly what we did in problem 23. And we're going to plug in the critical point and the endpoints and make sure that the maximum output is at x equals 100. So let's do a of 0. And a of 0 is just 0. And then a of 200. And a of 200 is equal to 0 as well, I believe. Yeah. And then let's do a of 100. And a of 100, I don't even know, give me a second. $25,000. That is definitely the maximum output, which means that yes, x is the maximum. So x is equal to 100 yards. Awesome. And if x is 100 by our constraint, that means that y is going to be 500 minus 5/2 times 100. And 5/2 times 100 is 500 minus 250, which is 250 yards. And you're done. All right, any questions on this one? Okay. Let's see. I think I said I would do. Oh, another question just popped up. All right, hold on. Oh, okay, so I got a question on how I got 200 again. Okay, so when you're looking for the domain here, in this case, you're looking for any values that you can plug in for x. So sometimes it's helpful to go back and think about what x actually is. So x is these like vertical lengths here in the middle. So let me go ahead and highlight them. So Okay, so this is X, this is X, this is X, this is X, and this is X. So it's like, what can I actually plug in for X? Okay, well, you could plug in 0. That literally would give you a completely flat rectangular region. Like it's just fencing alongside fencing because there's no like width to it. If X is 0 and you don't actually like have any lengths here, I mean, it's dumb, but you could do it. It's definitely not going to maximize it, but it doesn't matter. What could you plug in for X? Sure, you could make X 0. So weird choice. Or, so that's like one extreme. You use none of the fencing on the X's, or you use all of the fencing on the X's. Okay, if you use all 1,000 yards of fencing on these X's right here, you have 5 X's and 1,000 yards of fencing. So that means that each X would be 200. So that's how I got 200, because 1,000 divided by 5 is 200. So it's just like kind of the extremes here. X can either be 0 and you use no fencing on X, or it could be 200 where you've used all the fencing on the X's. Neither of them are good options, because if you use all of it or none of it, you don't get any like area that's enclosed. It's very weird. So even though it may not be the logical choice for X, that's still the domain because it could be true. Okay. Let me do 28 because that's a newer question that was asked. Oh, good times. Okay, linear approximation, something different. Okay. Oh, sorry, guys. Okay. So use the linear approximation method to estimate the value of the cube root of 28. Okay. So let me bring up the linear approximation like theorem, or like I think it would just be helpful to like look at what it says, if there's even a theorem. I'm not sure. That's not like super helpful. Okay, well, basically linear approximation says that if you want to approximate a function, so you're given a function and you want to approximate it at a certain value. We're given both of those pieces of information combined in this problem, so that could be why maybe it is kind of confusing. So usually you're given like an f of x, and then you're told approximate it at this value or at this input. Both of those pieces are given to us together in this problem, so we're told that we want to approximate the cube root of 28. So that would make our f of x equal to the cube root of x, and we want to approximate it where x is 28. So, actually, let me like write that a little better. So approximate at x equals 28. Okay, so you want to approximate what that output is, and there's a method of using linear approximation, and what this says is, hey, if you want to approximate this function at 28, why don't you find the tangent line like really close to 28, basically. So it says to go ahead and find the tangent line at some point that is very close to 28. So sometimes you're told to find it at like, let me find another example so this makes sense. Like in the one above it, you're told to do a linear approximation at 1.1. And so you find the tangent line at 1. So you usually just pick a value that's close to what you're being told to approximate. And most of these examples, they're like decimals. So like 1.99, you would pick 2, 1.1, you pick 1. However, in question 28, it's a whole number and it's 20. Well, that's ironic, 28, 28. Sorry. So you're given a whole number. It's not really clear like what you should find the tangent line at. So I'm just going to pick 27. It's close to 28. That's fine. The closer the tangent line to what you're approximating, the better. But that's fine. We'll just use 27. So our goal is to 1, find tangent line at x equals 27. So the reason it's called linear approximation is because the cube root of x is not a linear function. It's not a line. It's a cube root, and it's not a straight line at all, but we can approximate it with a line, which is the tangent line. That's why it's called linear approximation. So you're finding the tangent line at some value close to what you're approximating. And you're saying, hey, this actually is close to what the actual value is. Kind of cool. So let's go ahead and find the tangent line at x equals 27. This is a process that we've done before many times. You'll never escape it. They just keep renaming it and using it in different things. So let's go ahead and do that. So whenever we're finding a tangent line, we have y minus y1 equals m times x minus x1. I think I've probably written this down maybe 100 times this semester. Never gets old. So first of all, we want to find y1, m, and x1. You're given x1 because we're finding the tangent line at 27. To find y1, we're going to do the cube root of 27. And this is a little hint that maybe this is why picking 27 is a good idea, because there's actually a cube root of 27. If you were to pick like 29, that's not the nicest number, but 27 has a nice cube root, so it's a good reason for why that was a nice number to pick. And the cube root of 27 is actually just 3. Lastly, we need to find m, which is the derivative at x1, which is 3. But first, we should actually find the derivative because we don't know that. So I'm going to do that off to the side. So f of x is equal to the cube root of x, which is also x to the 1/3, which makes f prime of x equal to 1/3 x to the negative 2/3, which is also 1 over 3 x to the 2/3, which is also the same as 1 over 3 cube root of x squared. Okay, so let's go ahead and now find f prime of 3. So that means we're plugging 3 in here. Did I do this right? Hold on. Hold on, give me 1 second. Oh, I'm so sorry. I put 3. This should be 27. No wonder. I was really confused. Sorry, I accidentally put the 3 when it should be 27 because we're finding the tangent line at 27. My bad. Hopefully everyone realizes that I made a mistake. No wonder this wasn't working out. I was like, that's not a nice number. Okay, sorry. That should be 27 because x1 is 27. Whoops. Okay. So f prime of 27. Feel free to call me out if you ever see me make an error. It's easier than me like trying to figure out what I did wrong because, you know, I'm human. It happens. So feel free to call me out if you ever see it. I welcome it. So, anyways, so 1 over 3 the cube root of x squared, which is 27 squared. Okay, 27 squared is 729. And if you do some simplification, this is 3, and the cube root of 729 is 27. Yay. So this ends up being, hold on. What did I do wrong here? Oh my gosh, what am I doing wrong? Okay. That's what I'm doing wrong. This is 9. Sorry, the cube root of 729 is 9. Ooh, it's been a long day when I can't do algebra. Okay. And this is 1 over 27. Ooh, sorry, everyone. Okay. So 1 over 27 is your slope. Okay, great. So now the tangent line is y minus 3 equals 1 over 27 times x minus 27. I think I got that one right. Yes. Okay. Cool. And the last step of linear approximation is not too bad. Actually, it just says to plug in. whatever you are approximating. So we're approximating 28. So it just says to go ahead and plug that in. But there is another step, and it says to solve for y, essentially. This is just like a formality. So you get y is equal to 1 over 27, x minus 27 plus 3. And then it wants you just to change y to be L of x is equal to 1 over 27, x minus 27 plus 3. This is just like a formality. L of x is like the linear approximation at x. So that's just like an added step here. And then your last step is to just plug in 28 into this function. So L of 28 is equal to 1 over 27 times 28 minus 27 plus 3, which ends up being 1 over 27. My writing is just getting worse as we go on. Plus 3, which is 1 over 27 plus 81 over 27, which is 82 over 27. Woo. All right. So we arrived at our answer. I feel like that one was a little rough, guys. So let me just like recap what I did. So linear approximation, you will be given a function and what you are trying to approximate the value at. So in our case, our function was the cube root of x, and we were told to estimate the value at 28 because we were told to estimate the cube root of 28. So once you figure out what you're doing, you go ahead and find the tangent line of a value that is, or at a value that is close to what you're approximating. So we were told to approximate at x equals 28. So we're going to go ahead and find a tangent line at x equals 27, because that's close to 28. You go ahead and find the tangent line, boom, and then you just plug in what you're trying to estimate. So you plug in 28, because that's what we were told to estimate. Anyone have any questions on this process? Sorry that that one was a little rough. Okay, well, since it is now 7:30, I am going to end here on this problem, but are there any last minute questions?
Yep, thank you.
You're welcome. Good luck with your studying, guys. I will see some of you tomorrow. So thanks for coming, everyone. And I'll post this in case you want to watch it again or something. So bye, everyone.
All right, thank you very much.
You're welcome.